Any questions over the homework or any problems that y'all want to look at?
Did we get that last problem right?
Yes, there was one solution for it. The first problem where's that book? Let's see here, number 5, the third root of 8. Bigger if you can. So the first one was the third root of 8. And the cubed root of 8 would be 2. Now, is the root even or odd? Odd, because 3 would be odd. So this here is actually the answer. Because whenever we have an odd root, it doesn't matter if what's inside is negative, positive, or 0. We will only have one root. Whenever the root is even, that's where we could have one root, no roots, or 2. Because we won't have any roots if what's inside is negative. We'll only have one root if it's 0. And if it's greater than 0, then we would have 2. And what we're doing today is, again, just still delving more into what we did yesterday. In our first property, rational exponents, let a to the 1 over n be the nth root of a, and let m be a positive integer. Then we can say that a to the m over n is equal to a to the 1 over n times m, or the nth root of a to the m power. And our other property, a to the negative m over n, is really just utilizing our properties with negative exponents. So we would just move it to the denominator and do the exact same process. And both of these here are just manipulating the equations to make them easier to work with, especially if we're wanting to solve them or evaluate them without a calculator. Now our first expression here, 16 to the 3 halves. Now according to the property we just had, that a to the m over n is equal to a to the 1 over n to the m, or the nth root of a to the m. We can utilize this to be able to solve 16 to the 3 halves. Because what we can do is we can rewrite this as 16 to the 1 half to the third. Well, 16 to the 1 half is the same as saying the square root of 16 to the third. Because really this index here is 2. We don't necessarily write 2 because square root, it's understood to be a 2. And if we're looking for the square root of 16, what times itself is 16? Now we just need to find 4 to the third. Is 64. Four to the third power is 64. And that's it. So if we're doing these by hand and didn't use a calculator, this is one of the easier ways to work this, because we can break it apart and take it piece by piece, and it's a little bit easier to figure out. Any questions on the first one? Now let's look at the next one here, 32 to the negative 3/5. really to work with this, we need that exponent to be positive. And the only way to get an exponent to be positive is if we take the number from the numerator and put it into the denominator. Moving it from the numerator to the denominator, or denominator to the numerator, will change the exponent from being positive to negative, or negative to positive. Now we can do the exact same thing we just did with the other one, because we can say this is 1 over 32 to the 1/5 cubed. Now to find the 5th root of 32, because 32 to the 1/5 is the 5th root of 32, we need to see what times itself 5 times is 32 if we want to simplify this. We can factor tree, as we can say 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. 1, 2, 3, 4, 5. So the 5th root of 32 is 2. Because really what we're saying here is that we have 2 to the 5th to the 1/5, which is 2 to the 5/5, which is just 2. Because powers of powers multiply together, so 5 times 1/5 would be 5/5. 5 divided by 5 is 1.
So you just try to find
To the,
remaining statement.
yeah, so we could take the 5th root of it. Now, most likely, unless it specifically says to use a calculator, there's a good chance we can do it this way. If it's telling us that we need to use a calculator to do it, odds are that the root won't come out to be a whole number. Because there are numbers we can't take the 5th root of. Because if it had been 1 more, 33, it doesn't work. Now, the last thing we need to do is apply the 3rd power, because we have 2 to the 3rd, should be 8. So our final answer is 1/8. (32) to the -3 divided by 5. Is that the same thing we got? Well, that's a decimal, isn't it? So we can go math, enter, enter, we get 1/8. Because it is a nice root, it does work out this way. The only time we'll have issues doing it this way is if it wants it in simplest radical form. That means we have to leave it as a radical, not as a decimal. Okay. So here, if we wanted to utilize that breaking it apart property, we can really say that 64 to the 4/3 is the same as 64 to the 1/3 to the 4th. So 64 to the 1/3 is the same as saying the cubed root of 64, because 1/3 power and the cubed root are the exact same thing. So at this point here, we're really saying that I'm taking the cubed root of 64. I'm trying to find out what number times itself 3 times would give us 64. That's actually 4. Now we could do a factor tree, and I believe if we did a factor tree for 64, most of us would look at 2. Because this would be 2 times 32, and this would be 2 times 16, 2 times 8, 2 times 4, and then 2 times 2. And we've got all these 2's. We have 1, 2, 3, 4, 5, 6, yes? So, really inside here, if we did it this way, we would be saying that I have 2 to the 6 for the 1/3 to the 4th. Now, if you're thinking, well, we said 4 before, we'll actually get to the same place. Because at this point, powers of powers multiply. 6 times 1/3 would be 6 thirds, yes? 6 divided by 3 is what? Two squared is 4. So it took us 1 down further, but we still get back to the same place. And lastly, we have to do 4 to the 4th. Six, carry the 1. I think it's 256. But we could have also done 64 to the 4/3, and it would have told us that it's 256. For the other one, anytime we have a negative exponent, I know the first thing I'm going to have to do is move it from the numerator to the denominator. And that gives us 5/4. And we can break it apart and say 16 to the 1/4 to the 5th. Well, we do need to find the 4th root of 16. And the 4th root of 16 would be 2, because 2 to the 4th is 16. Because again, what we're saying, kind of off to the side, what we didn't write is, well, we have 2 to the 4th to the 1/4, which is 2 to the 4/4, which is just going to be 2. Well, 2 to the 5th is 1/32. And again, we could have plugged that into the calculator and gotten to the same answer. But again, I want to do this stepped out so that we can see how this property works, why it works this way. Any other questions on this here? Evaluate each expression using a calculator. Round your answer to 2 decimal places. So most likely, these are not going to come out to be whole numbers. And especially with the first one, 9 to the 1/5. So we're trying to look for a number that multiplied by itself 5 times gives us 9. Well, that's definitely not going to be a whole number. 9 to the 1 divided by 5. 1.55184. 5574. It continues on. But it only wanted 2 decimal places, so we're looking at 1.55. And that'd be it. The next one that we have is 12 to the 3/8. And the number after 3, I think, is a 6 or greater. Yep, so we would round up. And really, on all of these here, if we're being particular about it, we would put a 0 after it. You all know why. So it stops, it's more signifying that this is not the exact value. I rounded from the next one over. Because when we round up or down, it goes to 0. It's kind of a way to signify we rounded, because otherwise there's no point in actually putting that 0 there. And the last one, if we type this in, 30. And that one definitely shows we rounded, because the place after it rounded that one up to 10, which moved 1 over. Any questions on this here? I feel like we feel good with this here, yes? All right. The last thing we're going to look at today is solving equations using roots. Now, we've done this before. We called it the square root method, because we got the variable or set of parentheses that had the exponent by itself, and then took the square root of both sides and finished solving. Here, we're going to do the exact same process, except we're not going to be just using square roots. So for our first one here, we have 4 times x to the 5th is equal to 128. Now, it's only wanting us to find the real roots. Now, the first thing we need to do is to get the variable by itself, or set of parentheses to the exponent by itself. So here, with our 4x to the 5th is equal to 128, what do we think we need to do first? By 4. So it'll tell us that x to the 5th is going to equal 32. And at this point here, we wouldn't square root 5th root. Yeah, the 5 root. We would want to take the 5th root of both sides, because we have x to the 5th. Because what's happening on the left-hand side, because here we can just say that these mark out, which leaves us with x is equal to 2. But really what we're not saying, or kind of working out, is that really that this is saying that I have x to the 5th to the 1/5. Powers of powers multiply, telling us that we have x to the 5/5, which is just x to the 1st. This is why when we took the square root of both sides, the x squared and the square root just simplified out. And again, when we first covered that, writing a radical to a fractional exponent is a little bit much to throw on top of just taking the square root of both sides. So we use that shortcut instead. Okay. Now, before we say that this is it, is the root even or odd?
So plus or minus?
Odd. Because the root for this is what? 5. 5 is odd, so we either going to have one real root, or one real root. Because if it's odd, in any case, if what's inside is negative, it's only 1. If it's 0, it's only 1. If it's positive, it's only 1. And this is really breaking down the fact that we only have how many terms inside the root? 1. We only have one number. So it's only going to be one real root in any case. This is not saying that any kind of 5th degree polynomial is only going to have one real root. But we only have what here? X to the 5th. The times where we'll get more than that with odd powers is if we also have a even 4th, x to the 4th, x to the 3rd, x squared, x, and our constant. If we have all the other ones, then it kind of changes how it works. But if we just have this x to the 5th and take the 5th root, only one real root is going to work. Then that real root is 2. That means we also have 4 complex roots because of our the fundamental theorem of algebra. The degree tells us how many solutions we have. 5. We know only one of them's real. The other 4 have to be complex. Okay. Feeling it would scroll. Let's look at this one here next. Well, there are 2 ways we can go about it. One of them's harder than the other. The harder route is that I can take that x minus 3 and multiply it by itself 4 times. So 4. So we can multiply x minus 3 by itself 4 times and get the 4th degree polynomial function, but there's not a real point to it. Because over here, the only spot where x is inside those parentheses, isn't it? So there's no real point for me to multiply it out. If we had 21x or plus x somewhere where x was added outside, okay, then we would need to. But here, what I can do is apply the what root? 4th root. And this one I'm going to write out because it's going to make a little more sense, because this seems really funky of why we can do this. Because the left side, really what we just said is that I have x minus 3 to the 4th to the what? 1/4. Because any radical can be rewritten as an nth root, and we get this here. I'm going to leave that as the 4th root of 21. Because if I was a gambling man, I would guess that that's not going to be a whole number. Now, here we have powers of powers that multiply. Really what I have is x minus 3 to the 4/4. Well, 4 divided by 4 is 1. So really what that leaves us with is minus 3. Really, we could put parentheses to the first, but the first power doesn't change anything. Is equal to the 4th root of 21, yes? Wait a minute. Is our root even or odd? Even, because the number inside the root is 4. Okay, so this is the one that causes some issues, because this root could be positive or, because if the root is even and the number inside is positive, we have a positive or negative case. If the number inside is negative, we have no real roots, and we could have been done 3 steps ago. And if it's 0, well, it's just going to be 0. Because if we take the square root or cube root, any root of 0, it's just 0. Now the last thing we need to do is we still need to get x by itself. So we would add 3. Since the 3 is being subtracted, we do the inverse operation, which would be addition. So x is equal to 3 plus or minus the 4th root of 21. And it just said to solve, yes? Did it say to round? That's it. Because as we can try it, the 4th root of 21 to the 1/4, 2.14069, it does not have a whole number answer. So if it doesn't ask us to round or approximate, we can leave it with the radical. If the radical does simplify to a nice whole number, we're going to need to work it all the way through. Any questions on this? And that's it. That's all we have to do for this here. Let's look at one more of each with the with parentheses, one with and one without. So looking at this here, find the real solutions of 5x cubed equals 320. What would be our first step? Divide by 5. Because the 5x cubed divided by 5 would just be x cubed. 5 divided by 5 is 1. 320 divided by 5 is 64. What next? So we wouldn't use square roots, we would use cubed roots. Since x is to the third power, we would want to use a cubed root. Do we need the plus or minus? Because it's an odd root, so it would just be saying that x is equal to 4. Yeah. Any questions on this one here before we look at that one? So let's skip this one for a second and let's go to this one. Because I want to skip the parentheses so we can look at another one without. That way we can kind of keep them together. 8x cubed equals 64. So since x cubed is really the only term, we would want to get it by itself. We don't have to add or subtract anything. The first thing we can do is just divide both sides by 8, which tells us that x cubed is equal to 8. Then what can we do? We can cubed root both sides. Now for this one here, would we have the plus or minus? Because it's an odd root. We took the cubed root. Since it's odd, we would only have one possible solution. And this works with negatives because, again, we're multiplying the same number by itself an odd number of times. A negative times a negative is that's an even number, right? So one more, 3 would be negative again, yes? So it'd go back to being negative if it's inside, because as long as we have a number of negatives, it'll stay negative. And then, so it's just 2. Questions on this here? Now we can move back to this one here. This thing here. No. This one. I want this one. Because I didn't want to do the last one, that other one, because, again, it was an even root, which is nice, but it didn't come out to be a whole number. This one, on the other hand, will. Now, with the set of parentheses, we would want to move everything else away, just like when we did square, or when we did the square root of both sides, our square root method. So if there had been a number in front of the parentheses, so if we had a 2 out here, we would divide both sides by 2 and solve. But we don't. If we had something added or subtracted to it, well, we would subtract or add the opposite operation to get the parentheses by itself. That's the key goal. Because once we get these parentheses by themselves, what can we do? We can take the almost 4th root. Because we have the 4th power, we're going to take the 4th root. When we did the square root method, we used square roots because the exponent was a 2. And kind of going by our shortcut, these cancel because really we're saying that we are applying or multiplying it by the 1/4 power. So it tells us that x plus 5 is equal to 2, because 2 to the 4th is 16. Do we need the plus or minus? Yes. We can take the root because the 16 is positive. We know that we don't have one root because the only way that we can have one root with an even exponent is if the number inside is 0. Well, it's not 0, so we have to add the plus or minus. Well, last but not least, we need to subtract 5 because we do need to get x by itself. And if we subtract 5 from both sides, we get that x is equal to negative 5 plus or minus 2, yes? Now, on the last one that we had like this here, we circled it and said we were done, yes? But that's because we had the fourth root of, I think it was 21. Well, we figured out that didn't come out to be a whole number. So we really couldn't add or subtract those. Here, one way that we can look at it and kind of check to make sure to ourselves, can I do negative 5 plus 2? Well, negative 5 plus 2, I can add those two, yes? Can I subtract them? Negative 5 minus 2. So we need to take it a step further. Because really what we're saying is x is equal to negative 5 plus 2, and x is equal to negative 5 minus 2. Well, negative 5 plus 2 would be negative 3. And negative 5 minus 2 is negative. And those would be our two answers. And that's it. That's all we have to do with these. Questions on these here? And we do have more examples, but they don't really change.